afternoon to all of you. We start with our next session on kinematics of fluid flows, and the first item that we will discuss in this session is conservation of mass. Now, conservation of mass is very important. In the previous lecture, Professor Som described that how to describe a fluid flow in terms of its velocity components u, v and w, or maybe in some other coordinate system. Now, whatever may be the velocities, the velocity components must satisfy the law of conservation of mass. So, it is important to get a feel of the law of conservation of mass, how is it expressed in terms of its velocity components. So, to do that we will have several approaches. The first approach 1, let us say that we have the mass of a fluid element M which is nothing but density rho into volume V. This is following from the definition of density. Now, we take log of both sides and write ln of M is equal to ln of rho plus ln of V. Hence, now if we differentiate both sides with respect to time and we use the total derivative, which was already discussed in the previous lectures, that why the total derivative is important, because the total change is the sum of the change due to the change in time at a given location plus the change due to advection. So, the total change is given by the total derivative. So, we take total derivative of both sides. So, 1 by m dm dt is equal to 1 by rho d rho dt plus 1 by v dv dt. Okay. Now, let us try to simplify this equation. The first simplification is that this particular term dm dt is 0. Why dm dt is 0? Dm dt is 0 because for a system mass is conserved, that is the definition of a system. So, if mass is conserved, you must have the total derivative of mass with respect to time equal to 0. Next, we devote our attention to this term. What is this? This is nothing but the volumetric rate of strain, and the volumetric rate of strain, it was derived in one of the earlier lectures, that the volumetric rate of strain in terms of the velocity components are del u del x plus del v del y plus del w del z, where u, v and w are the velocity components along x, y and z directions respectively. Hence, we can write this equation as d rho dt, we are writing the right hand side first, d rho dt we multiply by rho. So, plus rho into 1 by v dv dt, 1 by v dv dt is del u del x plus del v del y plus del w del z, this is equal to 0. Now, let us simplify this d rho dt. D rho dt is nothing but del rho del t plus u del rho del x plus v del rho del y plus w del rho del z. So, the first term del rho del t is the change in density at a given location due to change in time, and the next three terms are changes in density because of encountering a different flow field at a given location, encountering a different density field at a new location because of advection with velocity components u, v and w. So, now let us simplify this equation. To simplify this equation, now what we can do, we can combine certain terms. You can combine rho del u del x with u del rho del x. If you combine these two terms, it becomes del del x of rho into u, the product rule of the derivative if we use. So, we write here first term del rho del t plus del del x of rho u plus similarly this box term and this box term, they together becomes del del y. So, this is rho del v del y, this is v del rho del y. So, del del y of rho v. Similarly, the last terms combined together, the terms which are ticked, these are combined together, del del z of rho w, this is equal to 0. Okay. So, we take it up from here. So, we write the equation again in this fresh sheet of paper, del rho del t plus del del x of rho u plus del del y of rho v plus del del z of rho w equal to 0. Now, let us try to learn how to write these equations in a compact vector calculus notation. So, we use the del operator. This del operator in a Cartesian system is I del del x plus j del del y plus k del del z, where I, j and k are unit vectors along x, y and z. So, now if we write the velocity vector v as ui plus vj plus wk, where u, v, w are the velocity components along x, y, z, then we make, if we make a dot product of del with v, the del operator with v, this is called as divergence of the velocity, divergence. So, if we write the divergence of the velocity, then if you make dot product of this, then it becomes del u del x plus del v del y plus del w del z. instead of V, if we write rho into V. So, in this equation instead of V we are writing rho V, that is rho ui plus rho Vj plus rho Wk. So, del dot rho V becomes del del x of rho u plus del del y of rho V plus del del z of rho w. So, you can see that this term or this collection of 3 terms we can write in a compact vector calculus notation as del dot rho V. So, del rho del t plus del dot rho V is equal to 0. This equation is a differential form of the conservation of mass, and this is known as the continuity equation. The continuity equation is a very important equation in fluid mechanics, because no matter how complex or how simple the flow field is, it must satisfy the continuity equation. We will give a deep physical interpretation to different forms of the continuity equation, different terms of the continuity equation, but before that let us use another approach to derive it, which is a control volume based approach. Approach 2. So, in this approach what we do, we consider a control volume. Let us take a small rectangular control volume. And let us designate some axis x, y and z. Now, this control volume has 6 faces. So, across these faces there will be some mass flow rate that comes in and there will be some mass flow rate that goes out. So, what is the balance? We can write m dot in. What is m dot in? M dot in is the rate of mass flow into the control volume minus m dot out m dot out is the rate of mass flow coming out of the control volume. Let us say that there is a control volume across which there is a mass flow rate that enters is say 10 kg per second, and there is a mass flow rate that goes out which is say 1 kg per second. If 10 kg per second comes in and 1 kg per second goes out, then this imbalance what it will do? Whatever is coming in, if it is not same as whatever is going out, the balance will give rise to a change in the mass of the control volume itself, right. So, let us say you have a tank and you are supplying some gas to the tank. Some gas is being supplied to the tank and some gas is taken out from the tank through a pipe. So, the difference between these two will give rise to the change in mass of gas within the tank. So, m dot, the tank is like a control volume. So, m dot in minus m dot out is nothing but rate of change of mass within the control volume. Why we are considering the partial derivative with respect to time? We are considering partial derivative with respect to time because we are fixing the position which is the control volume, and we are trying to see that what is the rate of change of mass at that fixed position within the control volume. So, now the next thing is, so this is a physical principle which all of us can intuitively understand. Now, we need to translate this physical principle in terms of mathematical expressions where the velocity components u, v, w and the density rho will be involved. So, to do that, let us say that the dimension of the control volume along x is delta x, dimension of the control volume along y is delta y, and the dimension of the control volume along z this is delta z. So, you can see that there are 6 faces, 2 faces have normal along x, 2 faces have normal along y and 2 faces have normal along z. So, let us give the names of these faces, say A, B, C, D, E, F, G, H. So, out of these faces you can see that if we shade these 2 faces, these are the faces across which fluid flow is taking place along x direction. So, m dot in minus m dot out, there will be some transport along x, some transport along y and some transport along z. To get the transport along x, we must consider these shaded areas because these areas have normal along x. So, these areas, flow through these areas will ensure that there is flow along x. So, what we do, we consider that there is, so what is the mass flow rate across this face? This red colored arrow indicates the mass flow rate across the face AEHD, AEHD, the shaded face. So, mass flow rate is the volume flow rate times the density. What is the volume flow rate? Volume flow rate is the velocity component along x times the area of the shaded face, which is delta y into delta z. So, this is the volume flow rate, that times rho is the mass flow rate. So, this in short symbol we call as m dot x. What comes out of the opposite face, let us write it clearly here. What comes out of the opposite face is nothing but m dot at x plus delta x. Our objective is to express mathematically m dot at x plus delta x in terms of m dot at x. So, it is like a mathematical function where we want to express the value of a function at x plus delta x in terms of the value of a function at x, and we do that by using something called as Taylor series expansion. Taylor series. So, as per Taylor series expansion, what is m dot x plus delta x? This is m dot x plus del x of m dot x into delta x plus terms of higher order delta x square, delta x cube, like that. So, we call it plus higher order terms. HOT, what I am writing, is a short form of higher order terms in the Taylor series. We will see later on that these higher order terms will not become important when we derive our equation. So, m dot x minus m dot x plus delta x, this is nothing but m dot in minus m dot out along x. So, that is minus del x of m dot x into delta x with higher order terms. Now, what is m dot x? M dot x is minus del x of, now m dot x is rho into u into delta y into delta z. Delta y and delta z are constant, so we can bring those out of the derivative. So, it becomes delta x into that delta y delta z. So, m dot in minus m dot out total is sum of m dot in minus m dot x plus m dot in minus m dot out y plus m dot in minus m dot out z. Okay. So, what we can write here, m dot in minus m dot out what was m dot in minus m dot out along x? That was minus del x of rho u into delta x into delta y into delta z, this is along x. Similarly, there will be a term along y, in place of x it will be y, in place of u it will be v, remaining terms will be the same. And similar term along z, v will be replaced by w. So, this is m dot in minus m dot out. Let us bring back the previous page just to recollect that m dot in minus m dot out, which we have just calculated, is nothing but del t of mass within the control volume. So, what is the mass within the control volume? This we will try to evaluate. What is the mass within the control volume? The mass within the control volume is nothing but the density times the volume of the control volume. So, rho into delta x into delta y into delta z. So, m dot in minus m dot out is equal to del t of rho into delta x delta y delta z. Because delta x delta y delta z are all constants, so that effectively becomes del rho del t into delta x delta y delta z. So, we do that. So, this is equal to del t of del t of rho into delta x delta y delta z. Remember, all these had plus higher order terms, plus or minus is irrelevant, some higher order terms in addition to this. Now, what we do, we take the limit as delta x delta y delta z tends to 0. Why we want to take that limit? We want to take that limit because we want to derive a differential equation. Remember, what is the physical meaning of a differential equation? Physical meaning of a differential equation is that some equality expressed in terms of differentials which are valid at a point. So, we must shrink our volume to a point where at which the differential equation must be applicable. So, we need to shrink our rectangular volume to a point. So, we can shrink that to a point if delta x, delta y, delta z, that is the sides of the rectangular element, rectangular parallelepiped to be in specific, the sides of that tend to 0. So, if we do that, then delta x, delta y, delta z gets cancelled from both sides, that is the first observation, and the higher order terms will have either delta x square or delta y square or delta z square or its higher powers. So, when you take the limit as delta x, delta y tends to 0 and cancel delta x, delta y, delta z, remaining delta x, delta y, delta z which remain in the higher order terms will become 0 in effect in the limit. So, we are left with the following: minus del del x of rho u minus del del y of rho v minus del del z of rho w is equal to del rho del t. So, if we take all the terms in one side, del rho del t plus del del x of rho u plus del del y of rho v plus del del z of rho w equal to 0, or in effect the shorthand notation del rho del t plus del dot rho v equal to 0. This is our continuity equation. So, it is another way of deriving the same equation which we considered from a system approach. So, we have in a nutshell we have shown two ways of deriving the continuity equation. There are several more ways, and it is what is important, like to learn a subject, the more number of ways in which you know how to derive an equation, the better physical insight you can derive on the equation. Now, next we will discuss on the continuity equation. This discussion is very critical and please listen to this very carefully. Special cases. Incompressible flow. Now, what is an incompressible flow? An incompressible flow is a flow in which there is no volumetric strain of a fluid element, because if there is a compressibility of a fluid element, that will be kinematically reflected in terms of a volumetric strain. So, no volumetric strain means 1 by V dV dt equal to 0, and that means del u del x plus del v del y plus del w del z is equal to 0, or divergence of the velocity vector is equal to 0. So, this is the consideration for incompressible flow. Now, let us try to apply this simplification to the continuity equation. So, the continuity equation, let me write it in the expanded form: del rho del t plus u del rho del x plus v del rho del y plus w del rho del z plus rho del u del x plus rho del v del y plus rho del w del z, this is equal to 0. Actually, I have expanded the equation this is nothing but del del x of rho u plus del del y of rho v plus del del z of rho w. So, now let us see that what is the simplification of this equation for incompressible flow. The first important observation is that for incompressible flow this term is 0, del u del x plus del v del y plus del w del z. For incompressible flow this term is 0. So, that means for incompressible flow we are left with this equation, del rho del t plus u del rho del x plus v del rho del y plus w del rho del z. This is equal to 0. So, what is this? This is nothing but total derivative of density is 0. So, let us come to a conceptual question. Is it necessary that for an incompressible flow the density has to be a constant? The clear answer is no. It is sufficient that if the density is constant then it is incompressible flow, but for the flow to be incompressible it is not necessary that the density has to be a constant, because you look into this box, the sum total of these 3 terms or 4 terms, sum total of these 4 terms has to be 0 for incompressible flow. So, it may so happen that the density varies in such a way that the combination of these 4 terms is 0, but individual terms are not 0. That means the density may be a function of position or time, the combination of the function of position and time is such that this is 0. And what kind of combination? The total derivative of density is 0. So, that the density can change because of 2 effects. One is because of the change of density at a given location due to change in time. The second is the change in density due to encountering a different density field at a given location as the fluid particle advex with the flow. So, the combination is a temporal term and the advective term which gives rise to the total derivative, and this total derivative of the density is 0 is a hallmark of incompressible flow. So, in books, in many of the very good books, they will write, since it is incompressible flow the density is constant. This is not totally correct. If it is incompressible flow, density is equal to constant is a special case, but variable density incompressible flow also may be possible. Let me give you a practical example. Let us say that there is a control volume in which there is a change in phase of a material, say melting, solidification, evaporation, condensation, and let us say that the densities of the 2 phases before and after phase change they are different. So, let us say that this control volume was occupied earlier by some liquid. Now, the same control volume is being occupied by a vapor as it is getting evaporated, and if the vapor volume the vapor density is less than the liquid density, what will happen? The vapor cannot occupy this volume. So, there will be some flow across this control surface to make a mass balance. So, you have a change in density because of flow plus a change in density at a given point of time, and if the flow is incompressible, the sum total of this effect is 0. If the flow is not incompressible, the sum total of this effect is not 0. So, it must be clear that an incompressible flow need not necessarily be a constant density flow. Okay. So we have discussed about a 3D incompressible flow. The next special case that we discuss is a 2-dimensional incompressible flow. Two-dimensional incompressible flow. Two-dimensional incompressible flow will mean that you have now incompressible flow requirement is del u del x plus del v del y. There could have been a plus del w del z, but two-dimensional flow will have only two velocity components u and v. So sum total of this is 0. This is a special case. Third special case which we commonly come across is steady flow. Steady flow means at a given location the fluid properties and the flow velocities do not vary with time. So in terms of the continuity equation, del rho del t is equal to 0. So you have del dot rho v equal to 0, that is the simplified continuity equation for steady flow. Now whenever you are introducing the continuity equation and whenever you are using continuity equation to maybe solve problems for your students, a very common form that comes to your mind is like A1 V1 equal to A2 V2. Like whenever continuity equation is mentioned, I have seen in many interviews or many viva voce examinations, we ask a student, what is the, can you write what is the continuity equation, or can you describe what is the continuity equation? The student will immediately say A1 V1 equal to A2 V2. So now whatever we have derived till now, it appears that as if it has no relationship with A1 V1 equal to A2 V2, but there is some important relationship, there is some interesting relationship, and in fact we can show that A1 V1 equal to A2 V2, with which you are very familiar, is also another form of continuity equation for some special case. So we will show that now. To show that, we consider a volume element, some arbitrary volume element, maybe if you like a diffuser, but it need not necessarily be like that. There is no flow which is taking place across the lateral surfaces, flow is taking place only across the surfaces 1 and 2. Now let us integrate the continuity equation del dot rho v. Let us first consider steady flow, that is an assumption. Del dot rho v equal to 0, let us integrate that with respect to the volume of this element, integrate over the control volume. As you can notice from our symbols, because both velocity and volume are v, so we are representing the volume by a v with a line in the middle, just to indicate that it is not velocity but it is volume. Now this is a volume integral, we will convert this volume integral to area integral by using a theorem in vector calculus known as divergence theorem. Just as a side remark, what we can say is that many of you may not be very comfortable with the notations of vector calculus, maybe you have gone through those long back. So this is a good scope to recapitulate. When we conducted the coordinators workshop, it was requested to us to have separate some separate sessions on like a review of vector calculus, but what we have decided is that instead of having a separate session which is unrelated to vector, unrelated to the concepts of fluid mechanics, we will give you concepts of vector calculus in the context in which they are appearing as we are moving through the discussion on fluid mechanics, and that is how we will proceed. So the divergence theorem, it relates the area integral with a volume integral. If f is a vector function and eta be a unit vector normal to an area area dA, then f dot eta dA is divergence of f dV. What is A? A is a control surface area which completely bounds the control volume. So the area integral and volume integral equivalence, this is true only when we are considering the CS as the control surface area which totally bounds the control volume. This is a very important consideration. So instead of f, now what we can see is that we have here del dot rho v. So f is equal to rho v. So we can write this as integral of CS, integral over CS rho v dot eta dA is equal to 0. Now what is the control surface area? Let us look into this. So here you have a control surface, here you have a control surface, this is a control surface, this is a control surface. So all together totally the surface which is bounding this volume is a control surface. Out of that there is flow only across 1 and 2, the remaining control surfaces do not have any flow across that. Therefore what we do, we only consider the surfaces 1 and 2 and write for the surface 1 rho v dot eta dA plus for the surface 2 rho v dot eta dA is equal to 0. Now let us consider the next assumption, that it is a one dimensional flow. When we say it is a one dimensional flow, we mean that the velocity vector has only one component, that is along x direction. So v is equal to u I cap, where u is the unit vector, where I is the unit vector along x direction. For the surface 1, for this surface 1, what is eta? What is unit vector normal to this surface? If this is the positive x direction, the unit vector in the outward normal to this surface is minus I, it is along the negative x direction. So v dot eta will be ui dot minus I, so minus u, and we also have for the surface 2 v dot eta, v is ui and eta for the surface 2 is along positive x direction. So v dot eta is plus u. So we can write this equation as integral of minus rho u dA for 1 plus integral of rho u dA for 2 is equal to 0. Now you can replace this in terms of the average rho u. If you define rho u average such that integral of rho u dA is equal to rho u average into A, and integral and the same for the section 1. So, rho u average 1 into A1 plus rho u average 2 into A2, this is equal to 0. If rho is also a constant, if rho is constant, then we can cancel rho from both sides and we can write A1 into u average 1 is equal to A2 into u average 2, if rho is constant, if rho is constant. So, this is like your A1 V1 is equal to A2 V2, A1 into u average 1. Remember, when you say A1 V1 equal to A2 V2 or A1 u average 1 is equal to A2 u average 2, it is u average. So, when you write V1, V1 does not mean velocity at a point 1, it means the average velocity over a cross section 1. So, the notation is very important. Many times the velocity at a point is same as the average velocity over a cross section. When is it true? It is true when the velocity profile is uniform. So, for uniform velocity profile, A1 V1 equal to A2 V2 is as good as A1 V average 1 is equal to A2 V average 2. So, what are the assumptions under which this is valid? It is steady flow, constant density flow and one dimensional flow. Okay. So, to summarize our discussion so far, we have introduced the continuity equation, we have shown two ways of deriving the continuity equation, we have derived the continuity equation, the special forms of the continuity equation for incompressible flow, and we have also shown its integral form. Now, the next agenda will be to discuss a special case when you have two dimensional incompressible flow. This special case we will discuss in much more details. So, two dimensional incompressible flow. So, the continuity equation is del u del x plus del v del y is equal to 0. Now, let us say you want to find out u and v. Now, there are two parameters in this equation. It may be convenient if we reduce these two parameters and express this in terms of a single parameter. So, in terms of that single parametric function, you could possibly replace u is equal to, let us say, del psi del y, where psi is a function of x and y, and v is equal to minus del psi del x. Then you can see that this equation, this continuity equation for two dimensional incompressible flow is automatically satisfied, because this becomes del square psi del x del y, this becomes minus del square psi del x del y. So, sum total of these two will become 0. So, if sum total of these two becomes 0, then we can say that the introduction of this function psi automatically satisfies the continuity equation, but not the general continuity equation, a special form of the continuity equation which is valid for two dimensional incompressible flow. So, this function psi is called as stream function. So, the definition of stream function, regarding the definition of stream function, we have to keep certain things in mind. First, we have defined u equal to del psi del y and v equal to minus del psi del x. Instead of this, we could define u equal to minus del psi del y and v equal to del psi del x. So, it is just a matter of sign convention, both are correct, but we have to adapt one. So, we are adapting u as del psi del y and v as minus del psi del x. If some book takes u equal to minus del psi del y and v equal to plus del psi del x, that also automatically satisfies the continuity equation and that is correct. So, psi equal to psi is defined for 2 dimensional incompressible flow. Now, question is, out of many possible names, why is this function called as stream function? So, let us calculate d psi. Remember that psi is a function of x and y. So, by rule of partial derivative, d psi is del psi del x into dx plus del psi del y into dy. So, what is del psi del x? That is minus v. So, minus v dx. What is del psi del y? That is u. So, plus u dy. Now, let us consider a line for which d psi equal to 0. D psi equal to 0 means psi equal to constant. So, what are psi equal to constant lines? If d psi equal to 0, you must have minus v dx plus u dy equal to 0. So, we can write dx by u is equal to dy by v. What is this? In the morning session you have been introduced to this. This is nothing but equation of a streamline for a 2 dimensional flow field. So, constant stream function means that you are actually referring to a streamline. So, that is why the name stream function. Now, here there is a very important thing that you must carefully note. The streamlines are defined for all kinds of flows, but stream function is not defined for all types of flows. The stream function that we have defined here is defined for 2 dimensional incompressible flow only. I mean, there are extensions of this definition which you can use for even 2 dimensional compressible flow. To avoid complications, we are not going into that, but you have to keep in mind that stream functions are defined only under restricted circumstances, whereas streamlines are defined for all types of flows. So, you have dx by u equal to dy by v. This is a consequence of the stream function, the d psi, the change of stream function, differential change of stream function equal to 0. Now, what we can do is that like we have gone through some theoretical exercise so far. So, we stop for a moment on going towards further theoretical derivations, and let us try to work out a very interesting problem. An example, let us say that this example is based on the discussions that we have made so far in the afternoon session. Let us say you have the density of a fluid given by kxy, rho is equal to kxy, where the units are adjusted in such a way that the unit of k is adjusted in such a way that it becomes the unit of density rho when k is multiplied with x and y. Let us say that we claim that it is an incompressible flow. Is it possible? 2D incompressible flow. If possible, then find out the equation of the streamline. So, see, this is not a very intuitive or not a very straightforward question, because the intuitive answer will be, well, rho is varying, so it is incompressible. Let us try to make an assessment of this. So, we have already discussed that the criterion for incompressibility is not rho equal to constant, but total derivative of rho equal to 0. So, del rho del t plus u del rho del x plus v del rho del y plus w del rho del z equal to 0. Now let us say that k is a time independent constant, so del rho del t is equal to 0 because rho is equal to kxy, it is not a function of time. It is a 2 dimensional flow field, it is given that it is a 2 dimensional flow field, so this term is 0. So what is del rho del x? Del rho del x is ky, and what is del rho del y? Del rho del y is kx. So u into ky plus v into kx is equal to 0. So u by v is equal to minus x by y. So if you have a velocity field where u by v is minus x by y, then rho equal to kxy could possibly represent a 2 dimensional incompressible flow. So and if you are interested to find out the equation of the streamline, it is straightforward, dx by u is equal to dy by v. That means dx dy is equal to u by v is equal to minus x by y. So dx by x plus dy by y is equal to 0. That means if you now integrate it, ln x plus ln y is equal to, let us say, some constant ln c. So xy equal to c. So that is the equation of the streamline. We next move on and we now discuss what is the physical interpretation of the stream function. So physical interpretation of the stream function. To understand that, let us consider that you have a small element dl. If it is differentially small, a curved element will approximately be a line element. So let us say that this is dl and it has a unit vector, outward normal vector as eta. Let us say that this is the x direction and this is the y direction. So this length is dx and this length is dy, and let us say that this angle is theta. So and let us say that the width perpendicular to the plane of the paper is b. B is width perpendicular to the plane of the paper. Okay. So what we do, we find out the volume flow rate across dl. So volume flow rate q across dl, this is the question that we would like to answer. So in terms of the vector components, the eta can be written as, so if you complete the vector triangle, the x component of eta, so the length of eta is 1. So, if this angle is theta, this angle is theta what is given, then this angle is theta, and then this angle is 90 degree minus theta. So, this angle is theta. So, this vector eta has an x component which is minus sin theta and y component which is cos theta. So, eta is equal to minus sin theta I plus cos theta j. Okay. And the velocity is uy plus vj. So, what is the q? Q is v dot eta into the area dl into b. So, what is v dot eta? That is minus, so v dot eta, dot product of these two vectors. So, minus u sin theta plus v cos theta, that into dl into b. Now, we can see from here, from this triangle ABC, from this triangle ABC, that sin theta is equal to dy dl and cos theta is dx dl. That means q is equal to minus u dy plus v dx, dl and dl cancel, into b. Writing in terms of the stream function, what is u? U is equal to del psi del y, and what is v? V is minus del psi del x. So, q is equal to minus del psi del y into dy plus del psi del x into dx. So, d psi into b. Instead of calling it q, we call it dq. Why we call it dq? Because we are considering flow across a differential element. So, instead of calling it q, we call it dq, and then if we integrate it, integral of dq, let us say from a point 1 to a point 2, this is nothing but integral d psi from 1 to 2 into b. So, what we get from here is the net q across 1 to 2 is mod of psi 2 minus psi 1, this is q by b. Integral of d psi is psi 2 minus psi 1, because we are interested about the magnitude of the flow rate, the sign is not important. So, q by b. So, what it means? The difference in stream function between the 2 points 1 and 2 physically represents the volume flow rate per unit width of a line element that connects 1 and 2. Okay. So, what we can conclude from here? What we can conclude from here? We can conclude from here is that if psi 1 is equal to psi 2, if psi 1 is equal to psi 2, then q by b equal to 0. If so, let me write it here. if psi 1 is equal to psi 2, then q by b equal to 0. So psi 1 equal to psi 2 means what? Psi 1 equal to psi 2 means the stream functions at the points 1 and 2 are equal, then there is no flow across 1 and across the line 1 2, because the line 1 2 then is a streamline. So a very important physical understanding from here is that along a streamline, since there is no difference in value of psi, there is no flow across a streamline, and therefore any line across which there is no flow can be visualized as a streamline. So the contour of a solid body is also a streamline. Let us say you put a circular cylinder in a flow, then the contour of the circular cylinder is also a streamline, because there cannot be any flow across it. So this is a discussion about the stream function. We will come back to the stream function again, but before that we introduce another important concept which is called as velocity potential. Now for that we recall the definition of vorticity. The vorticity zeta is defined as the curl of the velocity vector. This was discussed by Professor Som in his morning lecture. Now let us define some flow which is an irrotational flow. What is an irrotational flow? An irrotational flow is a flow which has no angular velocity, or in other words no vorticity. So because it has no vorticity, you have curl of the velocity vector as a null vector. Now from vector calculus we know that if curl of a vector function is a null vector, then the vector function can be written as the gradient of a scalar function. See this del operator, let me come to this operator for just for your understanding. We write del which is gradient, del dot which is divergence, and del cross which is curl. So this is gradient, this is divergence, this is curl. So this is, so when we write gradient of a scalar function, grad converts a scalar into a vector by means of a vector operation. So this phi is a scalar function, it is converted into a vector by the del operator. So we can write V is grad phi, not always but only when curl of the velocity vector is a null vector. So this phi is called as velocity potential. When is the velocity potential defined? Therefore the velocity potential is defined for an irrotational flow. The irrotational flow may be 2 dimensional, 3 dimensional, whatever, there is no restriction on dimensionality like the stream function. The velocity potential is defined for any flow provided it is irrotational. So velocity, so let us summarize. The definition of stream function is that we have given is valid for 2 dimensional incompressible flow. The definition of velocity potential is valid for irrotational flow. So V is equal to grad phi. So grad phi means the del operator is I del x plus j del y plus k del z, and phi. So I del phi del x plus j del phi del y plus k del phi del z. So, this V is uy plus vj plus wk, this V. So, equating the components of the vector, the x component, y component and z component, we can write u is equal to del phi del x, v is equal to del phi del y and w is equal to del phi del z. Remember that these, just like psi equal to constant is called as a streamline, phi equal to constant is called as an equipotential line. Now, what is the relationship between an equipotential line and a streamline if both are defined? So, when streamline, remember streamline is always defined. Now, let us consider a 2-dimensional plus incompressible flow when stream function is defined. Streamline is defined always, but stream function is defined for this case, plus irrotational flow when phi is defined. Phi is a function of x, y and z such that u equal to del phi del x, v equal to del phi del y and w equal to del phi del z. So, when psi is defined, which is there for 2-dimensional incompressible flow, let us write what is d psi. D psi is del psi del x into dx plus del psi del y into dy. Remember the definition, u is equal to del psi del y and v is equal to minus del psi del x. So, del psi del x is minus v and del psi del y is u. So, psi equal to constant, that is d psi equal to 0, lines will have dy dx. So, if you set this equal to 0, dy dx is equal to v by u. Next, let us go to the issue of phi. Remember the definition, u equal to del phi del x and v equal to del phi del y. So, d phi is equal to del phi del x into dx plus del phi del y into dy. So, phi equal to constant or d phi equal to 0, this will mean dy dx. So, del phi del x is u and del phi del y is v. So, dy dx is equal to minus u by v. So, now let us come to these equations. This is for psi equal to constant, this is for phi equal to constant. So, dy dx for psi equal to constant times dy dx for phi equal to constant, what is that? What is that? That is V by u into minus u by v. So, what is dy dx? For a curve, dy dx represents the slope of the tangent. So, dy dx represents the slope of the tangent. So, you have a psi equal to constant, let us say this is psi equal to constant, and let us say this is phi equal to constant. So, let us consider their common points of intersection. At the common point, if we are drawing two tangents, to the two curves, the slopes of the tangents, if those are m1 and m2, then m1 into m2 is v by u into minus u by v. So, now at the common point of intersection, you have common u and common v, so u gets cancelled and v gets cancelled. So, this becomes minus 1. So, m1 m2 is equal to minus 1, that means these tangents are actually perpendicular to each other. This does not mean that the curves are perpendicular to each other. The correct technical terminology is the curves are orthogonal to each other. Orthogonal means their common tangents will be perpendicular to each other. So, we can say that in a flow field, when both phi and psi are defined, phi equal to constant lines and psi equal to constant lines are orthogonal to each other. When they are orthogonal to each other, we have to remember that there are some special points when this orthogonality is disturbed. What are those special points? See, here we have considered that there is division by u and v, but what is the situation when both u and v are 0? Those are points of singularity. That is, when u and v are 0, that is the velocity vector which is ui plus vj is a null vector, that means the point has no velocity, the point in the flow field has no flow velocity, that is called as stagnation point. So, at the stagnation point, this orthogonality cannot be described. So, we can say that phi equal to constant lines and psi equal to constant lines are orthogonal to each other everywhere in the flow field, except we cannot make this conclusion for the stagnation point. Okay. Now, the next issue is, and this is the final point that we discuss in this session, before that before we work out a problem and then make a closer to the session, is that what is the governing differential equation for phi and psi when both are defined. So, let us say when both are defined, u is equal to del psi del y, v is equal to minus del psi del x. How did we derive this form? We derived this form from the continuity equation. But when both phi and psi are defined, it must also be an irrotational flow. So, when it is an irrotational flow, you must have del v del x minus del u del y equal to 0. This is the vorticity or double of the angular velocity vector component with respect to rotation with respect to the z axis. This was derived by Professor Som in the morning lecture. Now, you look into the definition of u equal to del psi del y and v is equal to minus del psi del x. So, in place of v, if you write minus del psi del x, So, this becomes minus del square psi del x square, and in place of u if we substitute del psi del y, this becomes minus del square psi del y square. So, you have minus del square psi del x square plus and del square psi del y square together equal to 0. So, we can write del square psi is equal to 0, where del square is called as the Laplacian operator in vector calculus, Laplacian. So, it is del square del x square plus del square del y square plus del square del z square. Here it is a 2-dimensional flow, so del square del z square is not coming into the picture. So, this is the equation that is satisfied by the stream function when it is 2-dimensional plus incompressible plus irrotational flow. This equation del square psi, the Laplacian of a function equal to 0, this is called as Laplace equation in mathematical physics. This Laplace equation is not just there in the fluid mechanics, but it is also there in electrostatics and many other areas of physics. So, it is a very common equation in mathematical physics, and it is very important for anybody to know how to solve this equation. Now, let us look into the governing differential equation for phi. So, you have u equal to del phi del x, v equal to del phi del y. We are considering the 2-dimensional flow. So, these equations are from irrotationality constraint. Now, this u and v should satisfy the continuity equation also. Del u del x plus del v del y equal to 0. So, that means del square phi del x square plus del square phi del y square, this is del square phi del y square is equal to 0. That means del square phi equal to 0. So, our conclusion is that for 2-dimensional incompressible and irrotational flow, both phi and psi satisfy the Laplace equation. However, phi and psi are not the same because their boundary conditions are different, solutions are different. So, the functions may satisfy the same differential equation, but because the boundary conditions are different, their solutions are different, but the solutions when expressed in terms of visualization lines, the visualization lines will be orthogonal to each other. Now, to summarize what we have discussed, we have started in this session with the continuity equation. We have discussed the different ways of deriving the continuity equation and also its different forms, special consequences of incompressible flow and 2-dimensional incompressible flow as well as irrotational flow. For these cases we have defined two important functions, the stream function and the velocity potential. We have discussed about their physical significance and we have discussed about the governing differential equations describing their variations. Now, finally, I will work out a very simple problem to illustrate the calculation of stream function and the velocity potential before we come to a conclusion of this session. So, let us consider an example. Let us say that u equal to ax and v is equal to minus ay and w equal to 0. So, where a is having appropriate units to adjust the length unit to velocity unit. Now, is the flow 1-dimensional, 2-dimensional or 3-dimensional? is psi defined? If so, find psi. Third part, is phi defined? Psi and phi we mean stream function and velocity potential. If so, find phi. So, we start with the solution of this problem. It is a very simple problem, but it will illustrate how to make the calculations. Instead of going into more complex mathematical functions, we have used a simple mathematical function to illustrate the concept. Now, for the first part, it is clear that the velocity vector has two components, u and v, the third component is 0. So, it is a two dimensional velocity field. The answer to this part is straightforward. The second part, is psi defined? When is psi defined? Psi is defined for two dimensional incompressible flow. So, two dimensional we have already checked. Next question is it incompressible flow? So, 2D incompressible flow, how do you check? The equation that kinematically checks whether it is two dimensional and incompressible flow is del u del x plus del v del y. What is this? If it is 0, then it is two dimensional incompressible flow. So, del u del x is a because u is ax, del v del y is minus a because v is minus ay. So, sum total of this is 0. That means it is two dimensional incompressible flow. If it is two dimensional and incompressible flow, then the psi is defined. So, how do you find out psi? U is equal to del psi del y, that is equal to ax. So, what is psi? Now, there is a very important concept which I illustrate here. This is partial integration. When you integrate this with respect to y, then x is like a constant. So, when you write this is equal to axy plus not a constant plus a function of x, because with respect to differentiation with respect to y, a function of x is like a constant. So, this is 1. Then v is equal to minus del psi del x, that is equal to minus ay. That means psi is equal to axy plus a function of y. Now, if you compare the equations 1 and 2, you can write psi is equal to axy plus some constant, right. So, this is the form of the stream function. Now, this constant you can choose arbitrarily. For example, if you choose that at x equal to 0 and y equal to 0, psi equal to 0, then c will be 0, but that is a matter of your choosing the reference. Remember, stream functions, velocity, potential, these are all relative quantities. So, these depend on the choice of reference. If you choose that at x and y equal to 0, c equal to 0, then in this equation you will get c equal to 0, that is psi equal to axy. Next, let us go to the third part. Is phi defined? So, u is equal to del phi del x, v equal to del phi del y, this we know, but question is phi defined? So, how do you check whether phi is defined or not? You have to check whether it is an irrotational flow or not. So, if it is an irrotational flow, the angular velocity with respect to z axis will be 0. So, we have to check, is it true? That means del v del x minus del u del y equal to 0. Let us write the u and v again. U equal to ax, v is equal to minus ay. So what is del v del x? That is 0. What is del u del y? That is also 0. So this is 0. That means the angular velocity is 0. So that means the phi is defined. So u is equal to del phi del x. So Ax is equal to del phi del x. So phi we now integrate it, Ax square by 2 plus a function of y. This is equation number 3. Y function of y, again with respect to integration with or differentiation with respect to x, function of y is like a constant. Similarly, v is equal to minus ay is equal to del phi del y. So if you integrate with respect to y, this is minus a y square by 2 plus function of x. Now if you compare 3 and 4, we can clearly see, compare 3 and 4, this means f3y is equal to minus ay square by 2 and f4x is equal to ax square by 2. So phi is equal to a by 2 into x square minus y square. So far so good. Now it is important also to understand that this kind of flow is a very peculiar flow, and we will conclude this session by trying to visualize what kind of flow it is. So u equal to del phi del x is equal to ax is equal to del psi del y, v is equal to del phi del y is equal to minus ay is equal to minus del psi del x. This is what we have dealt with. Now we have found out that it is an irrotational flow, so the fluid element does not have rotation. Question is, does the fluid element have any shear deformation? To get a clue into that, the rate of shear deformation del v del x plus del u del y, del v del x is equal to 0, del u del y is equal to 0. That means the fluid has no shear deformation or no angular deformation. By shear deformation we mean angular deformation. So here is a fluid element which does not have any rotation, it does not have any angular deformation, but it has a volumetric strain. The volumetric strain is 0, the rate of volumetric strain is 0 because it is incompressible flow, but it has a linear strain which is non-zero. It does not have a volumetric strain, it does not have a non-zero volumetric strain, it has a volumetric strain which is equal to 0, but it has a linear strain which is not equal to 0, because what is the linear strain rate along x? Epsilon dot x is equal to del u del x, that is A. What is epsilon dot y? The linear strain rate along y, that is equal to minus A. Sum total of these we can call it epsilon dot xx and epsilon dot yy. So sum total of epsilon dot xx and epsilon dot yy is 0, that means it has no volumetric deformation, but it has linear deformation along x and linear deformation along y. If A is positive, it means it is stretching along x and it is contracting along y, but the volume of the fluid element is conserved. So this physical concept let us translate into a picture. So what is the equation of the streamline? We had already discussed, we had already seen what are the stream functions. So just to have your just to recapitulate, we had psi equal to axy. So constant stream lines, constant stream function lines or stream function lines is xy equal to constant. Xy equal to constant is a rectangular hyperbola, just like PV equal to constant in Boyle's law. So let us say that this is a rectangular hyperbola x y. So you have a fluid element, let us draw the fluid element. Let us say that we have a fluid element like this. When the fluid element is deforming, it is not rotating, so its orientation is not changing. It is not having angular deformation. So what is happening to it? You look into this one, it is stretching along x and it is contracting along y, but its orientation is remaining the same. So an originally rectangular fluid element will remain rectangular in this flow field, except for the fact that the rectangle will change its dimensions. Its length will increase if A is positive, its height will decrease such that its volume is conserved. That is what is a physical visualization of the kind of flow field that we have been talking about in this particular example. So with this we conclude our discussions on kinematics of fluid flows. We will take a short tea break now, and we will assemble at maybe 4 o'clock. We will assemble at 4 o'clock again, and the agenda of the session starting from 4 o'clock will be number 1, sharing with you the tutorial problems which have perhaps been shared with the coordinators of the respective units, and that is the respective centers, the nodal centers, and the other agenda will be taking up the questions that you have on the kinematics of fluids. So we will be happy to respond to your questions on various questions and queries on the kinematics of fluid flows in the next session. Thank you very much.